What if the scariest answer to the Fermi Paradox is not that we are alone, but that civilizations almost never last long enough to be heard? The universe is filled with stars, planets, oceans, chemistry, and time, yet every telescope, every radio dish, and every search still meets the same result: silence. Maybe life is common. Maybe intelligence appears more than once. But maybe the truly rare thing is a civilization that becomes technological, survives its own power, and stays visible across the stars. If you enjoy calm deep space documentaries like this, please like the video, subscribe to the channel, and share it with someone who loves the mysteries of the universe. The observable sky appears full before it appears silent. Across the night side of Earth, the stars seem to gather without end, spread through the dark as steady points of old light. Beyond them, telescopes reveal clouds of gas-cold dust, bright nebulae, and the pale shapes of other galaxies. The wider view is not empty. It is crowded with matter-motion radiation and time. Light crosses space from every direction, carrying signs of stars being born, stars dying, black holes feeding planets, passing in front of distant suns and ancient heat left from the early universe. Instruments above Earth and on the ground receive this light in many forms. Some collect radio waves, some collect infrared light, some measure visible light, ultraviolet light, X-rays or gamma rays. Each kind of light is part of the same broad family of radiation, and each tells a different part of the same cosmic story. Within this wide and active universe, the silence connected to the Fermi Paradox is not a complete absence of signals. It is a narrower silence. It is the lack of confirmed evidence for another technological civilization. Radio telescopes have listened for narrow signals that nature is not expected to make easily. Optical searches have looked for brief flashes that might come from powerful lasers. Infrared surveys have considered whether very large engineering projects could change the heat glow of a star system. Planet studies have searched for atmospheric gases that might suggest biology, while other efforts consider signs that might suggest industry. These searches are careful and limited. They do not cover all stars, all frequencies, all times, or all possible ways an unknown civilization might leave a trace. They cover selected parts of a vast space of possibilities. Within those selected parts, no detection has yet become accepted evidence. The silence is therefore a measured result, but not a final verdict. Observations indicate that strong, persistent, nearby and easily recognized signals are not common in the regions and ranges already searched. It remains uncertain whether faint signals, brief signals, distant signals, or unfamiliar signs are present beyond present limits. The difference matters. A quiet room may be empty, or it may contain a sound too soft to hear. A dark coastline may have no lamps, or the lamps may be hidden behind fog turned away, or too far for the eye. Astronomy works in this same careful way. It does not begin with certainty. It begins with what instruments can reach. Radio searches are often placed near the center of this silence, because radio waves travel well through interstellar space. They can cross long distances without being blocked strongly by dust. On Earth, radio technology also becomes a natural sign of a society that has learned to send information through the air and into space. A very narrow radio transmission concentrated into a small range of frequency can stand out from many natural sources. Nature produces radio waves in many ways, from charged particles moving through magnetic fields to storms around planets and activity near stars. Yet many natural radio sources spread their energy across wider ranges. A narrow and orderly signal may therefore attract attention. This does not mean that every narrow signal is artificial. Earth itself produces interference. Satellites, aircraft, ground transmitters, and instruments can create misleading traces. The search for meaning must pass through caution. Visible and infrared searches add other parts to the same outer layer. A distant civilization might not send a radio signal toward Earth. It might use light. It might produce waste heat. It might alter the brightness of its star in ways that look unusual. These ideas remain testable only in certain forms. Telescopes can measure a star's dimming when a planet passes in front of it. They can sometimes study the atmosphere of a planet by watching how starlight changes during that passage. They can survey the sky for objects that shine more warmly in infrared light than expected. Such methods are powerful, but they are not unlimited. A planet close to its star is hard to separate from glare. A weak atmospheric signal is hard to read across many light years. Dust can imitate heat. Natural systems can produce strange patterns. An unusual measurement is not enough by itself. It must survive repeated checks and simpler explanations. The outermost view of the paradox therefore begins with a calm mismatch. The universe contains many places where signals could in principle arise, yet the confirmed record remains empty. This emptiness is not dramatic in the instruments themselves. It appears as data without the expected mark. A search field is examined. Candidate signals appear and are removed. Some match human interference. Some cannot be repeated. Some come from known astrophysical sources. Some remain interesting for a time and then fade into uncertainty. The work continues because silence in science is still information. It can reduce the number of possible answers. It can show which kinds of signals are rare. It can guide better instruments toward better targets. The sky also carries background noise. Radio receivers hear the hiss of the cosmos, the glow of the Milky Way activity from the sun weather in Earth's atmosphere, and the growing clutter of human technology. Optical telescopes contend with clouds, moonlight, air, glow, dust, and the limits of detector sensitivity. Space telescopes avoid some of Earth's interference, but they face limits of size, time, and mission design. Every observation is shaped by the instrument that makes it. A telescope is not an open window onto everything. It is a filter built for certain wavelengths, certain brightness levels, and certain questions. At the larger scale, the silence becomes less like an answer and more like a boundary. It marks the distance between what is imagined and what is observed. The Fermi Paradox lives inside that boundary. It is not only about whether life exists elsewhere, it is about why a universe that seems able to make many planets has not yet presented a clear sign of other minds. In this first outer region, the only firm ground is the observable record. The record shows stars, galaxies, planets, radiation, chemistry, and motion. It shows no confirmed technological neighbour. This fact is simple, but its meaning is not simple. It may mean that detectable civilizations are very rare. It may mean that they are short-lived. It may mean that they do not produce signals that present searchers can recognize. It may mean that distance and time separate worlds too widely. It may mean that the search has only begun to touch the surface of the problem. The known result remains quiet and restrained. The sky is active in every physical sense, but silent in the one narrow sense that gives the paradox its weight. No accepted signal has yet crossed the line from possibility into evidence. The outer horizon stays bright with stars and dark with absence, and the measured silence remains the first region of the story. The Milky Way becomes the next region of the problem because the silence does not first need the whole universe. It can begin inside one galaxy. The Milky Way is the broad stellar system that contains the Sun-Earth, and nearly all stars visible to the unaided eye. From inside it, the galaxy appears as a pale band across dark skies, a soft river of unresolved stars and dust. From outside it would appear as a barred spiral galaxy, with a bright central region, long arms, clouds of gas lanes of dust, and a wide halo of older stars. It is not the largest galaxy known, and it is not unusually small. It is a mature, ordinary member of the cosmic population, and that ordinariness gives it importance. If ordinary galaxies can make planets and chemistry, then ordinary galaxies become natural places to consider life. The Milky Way is old enough for many generations of stars to have formed and died. Its age is measured in billions of years, and its history reaches far before the Sun exists. Stars form inside cold clouds where gas gathers under gravity. Some stars burn quickly and end violently. Some live calmly for immense spans of time. As the earlier stars age and die, they enrich space with heavier elements. In astronomy, heavier elements are elements beyond hydrogen and helium. These materials include carbon, oxygen, silicon, iron, and many other ingredients needed for rocky planets, oceans, atmospheres, and living chemistry. Later stars form from gas that carries this enrichment. The Sun belongs to this later history. It forms from material that has already passed through older stellar cycles. This long galactic timescale matters to the Fermi Paradox because it leaves room for many beginnings before Earth. The Sun is not among the first stars. Earth is not among the first rocky planets that could have formed. Observations and models indicate that planets are common around stars, and many stars in the Milky Way are older than the Sun. If some older stars have stable planets, and if some of those planets develop conditions that allow life, then the galaxy has time for histories much older than human history. The silence is therefore not only a question of distance, it is also a question of time. A galaxy with billions of years behind it seems wide enough and old enough for many attempts. The stars of the Milky Way are not evenly spread. Near the center, stars gather more densely and the environment can be more energetic. Farther out in the disk where the Sun resides, stars are more separated. Spiral arms contain clouds where new stars form, while the spaces between them hold older populations and thinner gas. The Sun lies in a quiet region of the galactic disk, not at the center and not at the outermost edge. This position offers a view through dust and stars, and it also places Earth in one local neighborhood among many. The nearest stars are only a few light years away, while the galaxy itself spans tens of thousands of light years. A light year is the distance light travels in 1 year. Even at light speed, crossing the Milky Way takes a long time. Distance stretches the meaning of contact. A signal sent from one side of the galaxy does not arrive quickly. It moves through space at the speed of light, yet the scale remains immense. A message from a star 1,000 light-years away arrives after 1,000 years. A reply takes another 1,000 years. Across the full galaxy, communication becomes a slow exchange between eras rather than between moments. This does not make detection impossible. It does make the galaxy feel less like a single room and more like an enormous landscape where events occur under different clocks. A civilization may rise signal change or disappear while its light is still travelling. The Milky Way also contains hazards. Massive stars explode as supernovae. Energetic radiation can affect nearby worlds. Dense regions may expose planets to more close stellar passages or stronger radiation backgrounds, yet the galaxy is not hostile everywhere. Many regions remain stable for long periods. The Sun has followed a steady path around the galactic center for billions of years. Other stars do the same. The existence of Earth shows that at least one region of the Milky Way can support a planet with long-lasting surface conditions. It does not prove that such regions are common, but it establishes that the galaxy can produce them. When scientists consider the number of possible sites for life in the Milky Way, The answer depends on many uncertain filters. There are many stars, but not all stars are alike. Some are too massive and short-lived to give planets long quiet intervals. Some are small and active, sending strong flares into nearby space. Some have few heavy elements. Some belong to binary systems where planetary orbits may be more complex. Yet none of these limits removes the whole field. The galaxy remains large enough that even a small fraction can still mean many worlds. This is one reason the paradox endures. The numbers do not need to be generous to become impressive. Even cautious estimates can leave a broad possibility. The shape of the galaxy also affects search. Human instruments see only part of it well. Dust blocks visible light across many directions, especially toward the center. Radio waves and infrared light can pass through dust more easily, but each method has its own limits. A star may be hidden by distance, crowding, or faintness. A planet may be too small or too close to its star to study. A signal may be directed elsewhere. The Milky Way is home, but it is not fully open to inspection. Much of it remains mapped in broad patterns rather than known in detail. In this galactic region, the Fermi Paradox becomes more contained and more serious. The question no longer rests on distant galaxies beyond practical reach. It rests on the same stellar system that holds Earth. The Milky Way has age material richness, quiet zones, countless stars, and enough time for complex histories. It also has distance dust danger and observational limits. These features do not settle the problem, they define its scale. The silence is not heard across a tiny sample of the cosmos alone. It is heard inside a galaxy that appears capable of making many long-lived places. The calm fact remains that no confirmed sign of another technological society has been found within it. The Milky Way surrounds Earth with light from ancient stars, and within that light the measured absence continues. Within the Milky Way the search narrows from stars to planets. A star alone is not a home for life. It is a source of heat, light, gravity, and radiation. Around many stars, smaller bodies travel in orbit shaped from disks of gas and dust left over after star formation. These bodies can become rocky planets, gas giants, icy worlds, moons, asteroids, and comets. For a long time, planets beyond the solar system remain unseen and uncertain. They are expected from theories of star formation, but expectation is not the same as observation. The first confirmed discoveries show that planets are not rare ornaments around a few special stars. They are a common result of the same physical process that makes stars. An exoplanet is a planet that orbits a star outside the solar system. Most known exoplanets are not seen directly as separate points of light. They are found through their effects. Some make their stars wobble slightly because star and planet both move around a shared center of mass. Some pass in front of their stars as seen from Earth and cause a tiny dip in brightness. Some bend the light of more distant stars through gravity. Some can be imaged directly when they are large, young, warm, and far enough from the glare of their stars. Each method finds certain kinds of worlds more easily than others. Large planets close to their stars are easier to detect than small planets far away. The known catalogue therefore reflects both nature and the limits of observation. Even with these limits, the result is clear. Planets are widespread. Many stars have them. Systems can be compact with several worlds packed close to their star. Other systems contain giant planets on wide orbits. Some planets are larger than Earth, but smaller than Neptune, a type not found in the solar system. Some are gas giants that orbit very near their stars, completing a year in only a few Earth days. Some are rocky in size, moving through regions where their temperatures may allow more complex surface conditions. The diversity is greater than early models expected. Planet formation is not a single neat pattern, repeated everywhere. It is a broad family of outcomes. This abundance changes the Fermi Paradox. If planets were rare, silence would be easier to understand. A galaxy full of stars but nearly empty of planets would provide few places for life to begin. Observations do not support that simple answer. The Milky Way appears to contain planets in very large numbers. The exact count remains uncertain because not every planet can be detected, but the scale is vast. Around common stars, worlds seem normal. This does not mean that Earth-like worlds are equally common. It means that the first necessary stage, the formation of planets, is not a narrow miracle. Planetary systems also show that location and arrangement matter. A planet's orbit controls how much light and heat it receives. Its size affects whether it can hold an atmosphere. Its composition shapes whether it has a solid surface, deep gas layers, thick ice, or a global ocean beneath ice. Nearby giant planets can disturb or protect smaller worlds, depending on their positions and histories. Moons can create tides. Asteroids and comets can deliver water and organics, but impacts can also disrupt surface environments. A planetary system is not only a list of worlds, it is a moving structure where gravity links each body to the others. The solar system provides one known example in detail. It contains rocky inner planets, gas giants, ice giants, dwarf planets, small bodies, rings and moons. Earth is the only known living world. Mars shows evidence of ancient water on its surface, but no confirmed life. Venus has a thick atmosphere and extreme surface heat. Icy moons around Jupiter and Saturn may contain oceans beneath frozen crusts. These nearby worlds show that planets and moons can hold many kinds of environments, even around one star. They also show that being a planet is not enough. The path from a formed world to a living world depends on many further conditions. Exoplanet studies make this lesson wider. Some planets orbit so close to their stars that their surfaces may be molten or their atmospheres stripped away. Some are likely locked with one side facing the star for long periods, although such worlds may still have possible climate patterns depending on their air and oceans. Some are so large that any solid surface lies far beneath deep layers of gas. Some may be water-rich with oceans much deeper than Earth's. Some orbit stars that flare strongly, especially small red stars. These stars are long-lived and common, but their early activity can be intense. It remains uncertain how often planets around them keep stable atmospheres and surface water. The abundance of planets therefore widens the field while adding filters. A large number of worlds does not directly become a large number of living worlds. Each world carries a history. It forms from certain material in a certain orbit around a certain star. It cools, changes, loses gases, gains, gases, receives impacts and responds to light and gravity. Its surface may become stable, or it may remain violent. Its atmosphere may shelter it, or it may trap too much heat, or it may vanish. The Fermi Paradox rests inside this difference between quantity and suitability. Many planets exist, but their ability to support life remains a separate question. The search for planets also affects the search for signals. A signal needs a source, and a source is more likely to be considered around a known star with known planets. Modern surveys create maps of targets. They reveal which nearby stars have small worlds which planets pass in front of their stars and which atmospheres may later be studied. Instead of listening blindly to the whole sky, researchers can choose systems with better reasons for attention. This makes the silence more meaningful in selected regions, but it still remains incomplete. Many planets are too distant or too faint for detailed study. Many do not pass in front of their stars from Earth's viewpoint. Many remain undiscovered. In this planetary region, the paradox becomes less about whether the galaxy has enough raw places and more about what those places are like. The Milky Way contains planets as a common feature of stars. The broad absence of confirmed technological signs does not come from an absence of worlds in general. It must be considered among worlds that vary widely in size, orbit, chemistry, and history. The quiet sky is therefore set against a crowded planetary background. Around star after star, gravity gathers material into bodies with surfaces, atmospheres, ice gas, and stone. The number of possible stages increases, but certainty does not. Observations indicate that planets are abundant. It remains uncertain how many are stable, temperate, wet, and chemically suited for life. The search moves inward from the simple existence of planets toward the narrower conditions that make a world more than a world. Within the broad population of planets, attention narrows toward regions where surface water may remain liquid. This region is often called the habitable zone. A habitable zone is not a guarantee of life. It is a range of distances from a star where a rocky planet with a suitable atmosphere may have temperatures that allow liquid water on its surface. The definition is cautious because water depends on more than distance alone. A planet too near its star may lose water or trap too much heat. A planet too far away may freeze at the surface. Between those limits lies a temperate band not fixed like a sharp ring, but shaped by the star, the planet, and the atmosphere that surrounds it. The idea begins with energy. A star sends light into space, and a planet receives only a small part of it. The amount depends on the star's brightness and the planet's orbit. A bright star can warm worlds from farther away. A faint star requires planets to orbit closer for the same amount of energy. The Sun's habitable zone is therefore not the same as the habitable zone around a smaller red star or a larger white star. The band moves inward or outward depending on stellar light. It also changes over time because stars do not shine with perfect steadiness through their whole lives. The Sun slowly grows brighter across billions of years. Other stars follow their own paths of change. Water gives this region its importance because all known life depends on it. Liquid water can dissolve many substances, carry molecules, support chemical reactions, and move heat. On Earth, water shapes climate, weather, rock, and living cells. This does not prove that life elsewhere must use water in exactly the same way, but water remains the most grounded guide because it is known to work. Scientists therefore use it as a practical search marker. A world in the habitable zone may deserve closer study, while a world far outside it may still be interesting but harder to connect to surface life as known on Earth. The inner edge of a habitable zone is controlled by heat and water loss. If a planet receives too much energy, more water enters the atmosphere as vapor. Water vapor is a greenhouse gas, meaning it helps trap heat near the surface. More heat can make more vapor, and more vapor can trap more heat. Under extreme conditions, a runaway greenhouse can occur in which oceans are lost and the surface becomes much hotter. Venus stands as a nearby warning. It is similar to Earth in size, but its dense atmosphere and strong greenhouse effect produce a surface far too hot for liquid water. The details of Venus's past remain under study, yet its present state shows that being rocky and near the Sun is not enough. The outer edge is controlled by cold and atmospheric warming. A planet far from its star receives less energy. Carbon dioxide can help warm such a planet because it also traps heat. On Earth, carbon dioxide is part of long-term climate regulation through the carbon cycle, in which air oceans, rocks, volcanoes, and living systems exchange carbon. A colder planet may hold more carbon dioxide in the air if geologic processes allow it, and this can extend the outer part of the habitable zone. Yet there are limits. Too much distance means too little sunlight. Carbon dioxide can condense or scatter light. Ice can spread and reflect more sunlight back into space. The surface may become globally frozen. A planet's atmosphere shifts the meaning of its orbit. Without air, a world has no strong blanket to move heat, hold pressure, or support stable surface water. With too little atmosphere, water may boil or freeze easily. With too much atmosphere, pressure and heat may become extreme. The kind of gases matters as much as the amount. Nitrogen can provide pressure without trapping much heat. Carbon dioxide and water vapor can warm. Methane can also warm under some conditions, although it changes under sunlight. Clouds complicate the picture because they can reflect light away or trap heat below. The habitable zone is therefore not only a distance zone, it is also a climate zone. The star itself shapes the band in further ways. Small red stars are common and long-lived. Their habitable zones lie close to them because they are dim. A close orbit can make a planet more likely to become tidally locked, with one side facing the star for long periods. This does not automatically remove habitability. An atmosphere or ocean may carry heat from the day side to the night side. However, close-in planets also face stronger effects from stellar flares, charged particles, and early high-energy radiation. Observations indicate that some small stars are active, especially when young. It remains uncertain how often their planets keep atmospheres that can support stable surface water. Larger, brighter stars place their habitable zones farther out, but they often live shorter lives. A star much more massive than the Sun burns its fuel quickly. Its light may be strong, but the time available for slow planetary and biological change may be limited. Stars somewhat like the Sun provide a balance that is well studied because Earth offers one example. Still, even among Sun-like stars, brightness, age, metallicity and activity vary. The habitable zone cannot be treated as a single universal distance. It is a moving estimate around each star. Known exoplanets show that many worlds orbit within estimated habitable zones. Some are roughly Earth-sized, some are larger, some orbit red stars. Some receive energy from their stars that may be similar to what Earth receives from the Sun. Yet these measurements are often incomplete. Radius may be known without mass. Orbit may be known without atmosphere. A planet may lie in the habitable zone and still be dry, airless, toxic, unstable, or covered by deep gas. It may also be hidden from present atmospheric study because its star is faint, distant, or too active. The label marks possibility, not conclusion. This distinction is central to the Fermi Paradox. Planet abundance makes many worlds possible, but habitable zone placement makes the field narrower. The silence cannot be explained simply by saying that temperate orbits do not exist. Observations indicate that planets in such orbits are present, yet the step from temperate orbit to living surface remains unresolved. The habitable zone is only an outer shell around the deeper requirements for life. It selects worlds where sunlight and distance may permit liquid water, but it does not answer whether water is present, whether atmospheres survive, whether chemistry becomes biological, or whether life changes a planet in detectable ways. In this region, the search becomes more careful and less broad. The galaxy does not offer only stars and planets. It offers stars with certain kinds of planetary orbits, and among those orbits are bands where water may endure. These bands are neither rare enough to end the paradox nor generous enough to solve it. They stand as quiet thresholds. A world inside one may be cold, warm, dry, wet, stable, or ruined. The evidence must come from further inward, from surfaces and atmospheres, rather than from distance alone. The measured silence remains now set against many possible temperate places where life could begin, but where the presence of life is still unknown. Inside the temperate band around a star, the question narrows again toward the stability of a world. A planet may receive a suitable amount of light and still fail to keep gentle surface conditions. Stability does not mean stillness. Earth is not still. Its air moves, oceans circulate, continents shift, volcanoes release gases, ice advances and retreats, and impacts arrive from space. Stability means that change remains within ranges that allow liquid water and living chemistry to persist across long periods. For the Fermi Paradox, this matters because life, and especially complex life, may require time. A world that is briefly mild and then permanently ruined may leave little chance for long biological development. A stable world begins with mass and gravity. A planet too small may struggle to hold a thick atmosphere over billions of years. Its interior may cool quickly, reducing volcanic activity and weakening long-term cycles between rocks and air. Mars shows this problem nearby. It has valleys, minerals, and surface features that indicate liquid water in the ancient past, but its present surface is cold, dry, and exposed under a thin atmosphere. Its lower gravity and changing interior are part of that history. A planet too large may hold a deeper atmosphere, stronger pressure, or layers of gas that make its surface very different from Earth's. Between these extremes, a rocky world can hold air support oceans and maintain geologic activity for long spans. The atmosphere is one of the main protectors of a surface. It provides pressure moves, heat shields the ground from some radiation, and allows water to exist as liquid over wide regions. It also links the surface to the star. Light enters heat leaves and gases decide how much warmth remains. A stable atmosphere is not simply a thick atmosphere. Venus has a thick atmosphere, yet its surface is extremely hot. Mars has a thin one, and liquid water is not stable across most of its surface today. Earth's atmosphere lies in a middle state shaped by geology, oceans, sunlight, and life. It contains nitrogen, oxygen, argon, water, vapor, carbon dioxide, and trace gases. Its composition is not fixed, but it has remained compatible with surface oceans for billions of years. Magnetic fields may help some planets keep their atmospheres. A magnetic field is a region of magnetic force produced in many planets by moving electrically conducting material inside the planet. Earth's field helps deflect some charged particles from the Sun. This does not create a perfect shield, and it is not the only factor in atmospheric survival. Venus lacks an Earth-like global magnetic field, and still has a dense atmosphere. Mars has only remnant crustal magnetism and has lost much of its ancient atmosphere. The relationship is complex. Gravity, atmospheric chemistry, volcanic supply, stellar activity, and distance from the star all matter. Observations indicate that magnetic fields can influence atmospheric loss, but they do not alone decide whether a planet remains habitable. The interior of a rocky planet is another quiet layer of stability. Heat from formation and radioactive decay can keep the interior active. This heat drives volcanism and, on Earth, plate tectonics. Plate tectonics is the movement of large pieces of the outer shell across the planet's surface. On Earth, this process recycles carbon between rocks, oceans, and the atmosphere. It helps regulate climate over very long times. When carbon dioxide builds up, weathering can draw some of it into rocks. When carbon becomes locked away, volcanoes can return some of it to the air. This cycle is slow, but on the timescale of life it is important. It can soften changes in stellar brightness and climate. It remains uncertain how common Earth-like plate tectonics is on rocky exoplanets. A planet may have volcanism without moving plates. It may have a stagnant outer shell. It may recycle gases in different ways. It may begin active and later slow down. The size of the planet, the amount of water, the composition of rock, and the heat inside all influence this behavior. Because exoplanet surfaces cannot yet be studied in such detail for most worlds, this stability filter remains partly hidden. A planet may look promising from its orbit and size, while its interior is unsuitable for long climate balance. Oceans also affect stability. Water stores heat, carries energy, shapes weather, and reacts with rock. A world with shallow seas and exposed continents may run a different climate cycle from one covered entirely by deep ocean. Continents on Earth provide minerals for weathering and nutrients for life. Deep global oceans may still be habitable, especially below the surface, but their long-term exchange with the atmosphere and rock could differ. Too little water can leave a dry world where chemistry is limited at the surface. Too much water can bury rock beneath immense pressure. Between dryness and deep water, there may be many possible climates, and Earth is only one example. A stable orbit also matters. A planet's path around its star may be nearly circular or more stretched. A stretched orbit can create stronger seasonal changes as the planet moves closer and farther from its star. The tilt of the planet's axis shapes seasons as well. Earth's tilt changes over time, but the variations remain within a range that life has endured. The Moon helps influence Earth's rotational behavior, but the exact importance of a large moon for long-term habitability remains uncertain. Some planets may keep stable tilts without such a moon. Others may experience stronger variations. Stability is again not a single requirement, but a pattern of interacting conditions. Impacts from asteroids and comets add another part of the picture. Early in a planetary system's history, impacts may be frequent and energetic. They can deliver water and organic molecules, but large impacts can also melt surfaces, strip atmospheres, or disrupt climates. Over time, impact rates often decrease as debris is cleared. Giant planets may alter impact patterns by scattering small bodies inward or outward. Their role can be protective in some cases and disruptive in others. The solar system's history shows both delivery and destruction. Earth survives impacts including major events, but its biosphere continues. A less stable world may not recover in the same way. For the Fermi Paradox, stable worlds form a narrower region than habitable zones. A planet may sit in the right band of light and still lose its air, freeze, overheat, dry out, or suffer constant disruption. A lasting biosphere may need a long balance among star orbit, atmosphere, ocean, rock, and interior heat. None of these elements has to be perfect, but together they must keep the surface within workable limits. Observations indicate that rocky planets exist in temperate regions. It remains uncertain how many of them maintain stable surface environments across billions of years. The silence therefore deepens in a calm way. The galaxy may hold many planets, and some may orbit where water could exist, yet only a smaller unknown share may remain steady enough for life to grow complex. Stability is not dramatic from a distance. It may appear as an atmosphere that does not vanish an ocean, that does not boil away a climate that does not collapse completely, and a crust that continues its slow exchange with air and water. These are quiet conditions easy to overlook beside stars and nebulae, but they shape the inner path toward life. The search moves from where planets are to how long they can remain gentle. Inside a stable world, the question narrows toward chemistry. A planet may hold oceans, air, rock, and steady light, yet life does not follow automatically. Chemistry must organize matter in a way that can preserve information, use energy, build structure, and make copies with variation. The beginning of life is called a biogenesis, meaning the rise of biology from non-living chemistry. It is not yet observed as a complete process in nature or in the laboratory. Experiments show that many building blocks of life can form under plausible conditions. Observations show that organic molecules exist in space, in meteorites, in icy bodies, and in planetary environments. It remains uncertain which path or which set of paths leads from those materials to the first living systems. The outer chemical environment begins with simple elements. Hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur, iron, magnesium, and other elements take part in living processes on Earth. Carbon is especially important because it can form many stable and flexible bonds. It can make chains, ring sheets, and complex three-dimensional shapes. Water helps these molecules meet, separate, fold, and react. Minerals provide surfaces where molecules can gather. Heat, ultraviolet light, lightning impacts, and chemical gradients can supply energy. A chemical gradient is a difference in concentration or energy from one place to another, and living cells use such differences to do work. Before cells exist, gradients may still drive reactions in rocks, oceans, and vents. Early Earth provides the only known natural setting where life begins, although its first details are not preserved clearly. The planet forms more than 4 billion years ago. Its surface changes under impacts volcanism, cooling crust, growing oceans, and a changing atmosphere. The oldest rocks are rare because plate tectonics recycles crust. Some ancient minerals indicate that liquid water exists very early. Fossil and chemical evidence suggest that life is present by at least several billion years ago, though the exact timing remains debated. This means that the transition from chemistry to biology happens within Earth's early history, but the conditions and sequence remain uncertain. Several environments are studied as possible settings. Shallow ponds may concentrate molecules as water evaporates and returns. Wet and dry cycles can help link small molecules into longer chains. Volcanic landscapes can provide heat and mineral surfaces. Hydrothermal vents on the seafloor can provide chemical energy, where hot fluids meet colder ocean water. Some vents form porous mineral structures, with tiny compartments, natural gradients, and steady flows. Icy environments may protect fragile molecules and slow reactions enough for some structures to survive. Impacts may deliver ingredients or create temporary warm settings. None of these settings is confirmed as the place where life begins. Each shows possible advantages and possible difficulties. The chemistry of life depends on large molecules. Proteins do much of the work in modern cells. They are built from amino acids folded into shapes that allow them to speed reactions, hold structures, and move materials. Nucleic acids such as ribonucleic acid and deoxyribonucleic acid store information. In modern life, deoxyribonucleic acid stores genetic instructions. Ribonucleic acid helps read and use those instructions, and proteins carry out many tasks. This system is deeply connected. A major problem for origin research is how a simpler system begins before the modern partnership exists. One idea studies ribonucleic acid because it can both store information and help reactions. Experiments show that ribonucleic acid can have catalytic behavior, meaning it can speed certain chemical reactions. It remains uncertain how such molecules first form in natural settings and how they become part of a self-sustaining system. Membranes add another inward step. A living cell is not just chemistry spread through water, it has a boundary. On Earth, cell membranes are made from molecules that naturally form thin layers, with one side attracted to water and another side avoiding water. Simple membrane-like bubbles can form from fatty molecules under some conditions. Such compartments can hold molecules together, protect them, and allow internal chemistry to differ from the surroundings. A compartment does not make life by itself, but it helps chemistry become local. Once reactions occur inside a boundary, changes within that boundary can matter to the whole structure. Growth division and inheritance become more possible. Energy use is equally important. Modern cells are not passive containers. They maintain order by taking in energy and releasing waste heat. Many life forms use sunlight. Others use chemical energy from rocks' gases or dissolved minerals. Very early life may have used chemical gradients before sunlight-driven biology becomes widespread. Minerals containing iron and sulfur can take part in reactions that resemble parts of modern metabolism. Metabolism is the set of chemical reactions that let a living system use energy and material. Origin research studies whether networks of metabolism-like reactions can arise before genetic systems, or whether information molecules come first. The answer remains uncertain, and both ideas may describe parts of a larger process. Organic molecules are not rare in the wider cosmos. Meteorites contain amino acids and other carbon-rich compounds. Interstellar clouds contain simple organic molecules. Comets and icy moons carry carbon compounds, water ice, and other ingredients. This shows that the raw materials for chemistry can be widespread. It does not show that life is widespread. Building blocks are not buildings. A planet may receive or form many organic molecules and still never organize them into self-replicating systems. The Fermi Paradox passes through this distinction. If organic chemistry is common but abiogenesis is rare, the galaxy may contain many promising worlds with no living surface. Laboratory work narrows the uncertainty without removing it. Experiments can make amino acids under certain gas mixtures and energy sources. Other experiments produce nucleotide components, lipid-like molecules, or reaction networks under controlled conditions. Researchers test mineral surfaces' wet and dry cycles, ultraviolet light alkaline vents, and many other paths. These studies show that prebiotic chemistry is active and varied. Prebiotic means before life. Yet the full bridge from simple chemistry to a living cell remains incomplete. A living system must combine information compartment energy flow and reproduction in a way that can evolve. Evolution requires variation that can be inherited and selected. Before that exist chemistry changes, but it does not yet evolve in the biological sense. This inner chemical region makes the silence more subtle. The galaxy may contain stable planets with water and organic molecules, but the first living system may require a sequence that is easy, difficult, or rare. Earth provides one success, but one success does not reveal the odds. Life may arise readily wherever conditions remain suitable. It may arise only under a narrow set of environments that Earth happened to provide. It may require many failed attempts before one system begins to evolve. Observations indicate that the ingredients and energy sources for life are common in many settings. It remains uncertain how often they cross the threshold into biology. In this region, the feared solution begins to take a quieter form. The silence may not come from the absence of planets or water. It may begin in the small spaces where molecules meet on rock, in pools in vents or under ice, where the difference between rich chemistry and living chemistry is difficult to measure. The first boundary may not be visible from space. It may be a microscopic transition hidden inside droplets, mineral pores, or warm sediments. Across the galaxy, many worlds may hold the right ingredients and still remain only chemical. The inward path now rests on whether matter can begin to remember copy and change. Inside the first threshold of living chemistry, the search narrows toward the simplest confirmed form of life. On Earth, life begins as microbial life made of organisms too small to see without magnification. A microbe is a living thing such as a bacterium, an archaeon, or a tiny single-celled eukaryote. The earliest life does not leave cities, bones, tools, or signals. It leaves subtle marks in rocks, chemical patterns, and layered structures that can be hard to interpret after billions of years. This matters for the Fermi Paradox because a living galaxy may not be a loud galaxy. If most life remains microbial, then many worlds may be biologically active without producing anything that telescopes can easily recognize as the work of minds. Microbial life is not simple in its chemistry, but it is simple in form compared with plants, animals, and technological species. A single cell holds a boundary genetic material and a working network of chemical reactions. It takes in energy, and matter maintains itself and reproduces. Some microbes use sunlight. Some use chemical energy from minerals, gases, or dissolved compounds. Some live in hot springs, deep rock ocean sediments, ice-acidic waters, salty lakes, and the dark seafloor. On Earth, microbes occupy nearly every environment where liquid water and usable energy persist. Their range shows that life once begun can adapt to many conditions. It does not show that life begins easily, but it shows that early life can spread widely after the threshold is crossed. The fossil record of the earliest life is difficult because the oldest rocks are rare and altered. Heat, pressure, erosion, and plate tectonics change or destroy ancient surfaces. Some evidence appears as carbon isotope patterns, because living processes can prefer lighter forms of carbon. Some appears as microscopic shapes that may be cells, though such shapes require caution. Some appears as stromatolites, layered structures formed when microbial communities trap and bind sediment. Stromatolites become clearer in rocks younger than the oldest debated evidence. Observations indicate that microbial life is ancient on Earth. It remains uncertain exactly when it begins and what the first organisms are like. The first living systems likely do not resemble modern cells in every detail. Modern bacteria and archaea are already highly evolved. They have refined membranes, enzymes, genetic codes, and molecular machines. The last universal common ancestor is the name given to the ancestral population from which all known life descends. It is not necessarily the first life. It is already part of a living lineage with shared features that survive in all life today. By the time this common ancestry can be inferred, evolution has already done much work. The true first life may be simpler, less efficient, and less stable than any organism now living. Early microbial life changes Earth slowly. At first, it may use chemical energy from the environment. Later, some microbes develop photosynthesis, a process that uses light to drive chemical reactions. Not all photosynthesis releases oxygen. Oxygen-producing photosynthesis associated with cyanobacteria eventually changes Earth's atmosphere in a major way. Before oxygen becomes abundant, Earth's air contains very little free oxygen. Much of the planet's chemistry is different. Iron dissolved in oceans can react with oxygen and form iron-rich layers in ancient rocks. Over long spans, oxygen accumulates in air and water, altering minerals' energy pathways and the future of life. This transformation takes time and does not happen immediately after life begins. The long microbial age of Earth is important. For most of Earth's history, life is present but remains dominated by microscopic organisms. Complex animals appear much later. For a distant observer during most of that time, Earth might show signs of biology in its atmosphere, but it would show no technology. It would be alive and silent. This fact gives the Fermi Paradox a grounded inner layer. A planet can succeed at life and still remain undetectable as a technological world for billions of years. The rise from life to intelligence is not a direct or automatic line. It passes through long intervals where bacteria and archaea are the main actors. Microbes also show that living worlds can be hidden below surfaces. On Earth, deep subsurface microbes live in rock pores and sediments using chemical energy far from sunlight. Life exists in the ocean crust beneath seafloors and in places where surface conditions are harsh. If similar life exists on Mars in the past or beneath icy moons today, it may not strongly alter an atmosphere in a visible way. A subsurface biosphere can be real and still quiet to distant instruments. This broadens the meaning of habitability while weakening the chance of easy detection. Living chemistry does not always announce itself from space. Biosignatures are signs that may indicate life. On a distant planet possible, biosignatures might include atmospheric gases that are hard to maintain without biology. Oxygen, ozone, methane, and other gases can be studied in combinations. A single gas rarely proves life because non-living processes can also produce or remove gases. The context matters. The star planet's surface, clouds, volcanism, water, and chemistry must all be considered. Earth's oxygen-rich atmosphere today would be a strong clue, but early Earth would be harder to identify. A microbial planet without oxygen producing photosynthesis may have weaker or more ambiguous signs. This creates a calm but serious difficulty. The most common form of life may also be the least visible. Microbes do not build radio transmitters. They do not reshape starlight through engineering. They do not create intentional signals. They may alter atmospheres, minerals, and surface colors, but those signs can be faint, uncertain, or hidden by clouds and distance. Even if a telescope finds a possible biosignature, the result may require years of confirmation and careful removal of non-living explanations. The search for life is not the same as the search for civilization. A galaxy with many microbial worlds may still look silent under searches for technology. On Earth, microbial life is also resilient. It survives mass extinctions that remove many larger organisms. It responds quickly to new environments because populations are large and generations can be short. It exchanges genes in ways that help adaptation. It forms mats, films, colonies, and communities that share resources. Its strength lies in smallness, number, and chemical flexibility. These traits may make microbial life more likely to endure than large complex life once it appears. If this pattern is common, living planets may spend most of their histories in microbial states. The Fermi Paradox passes inward through this biological quietness. The absence of confirmed technological signals does not mean the absence of life. It may mean that life when it appears usually remains at small scales, or takes immense time to change the planet in visible ways. Observations of Earth indicate that microbial life arises early enough to dominate for a vast period, while complex life arrives much later. It remains uncertain whether this timing is typical or unusual. With only one known living planet, the odds cannot be measured directly. In this region, the feared solution becomes less sudden and more patient. The galaxy may contain planets where chemistry crosses into biology, but biology may spend most of its existence as thin films, buried cells, ocean microbes, and mineral-fed communities under rock. Such worlds are not failures. They are alive in the deepest known sense, yet they do not answer the sky. They do not send structured light across interstellar space. They do not alter their stars. They simply persist, divide, adapt, and leave delicate marks in matter. The inner path now rests on whether microbial life often remains the final state, or whether it sometimes builds the larger cells needed for greater complexity. Inside the long microbial world, the next inward region is the rise of complex cells. A complex cell is a eukaryotic cell, a cell with internal compartments and a nucleus that holds genetic material. Plants, animals, fungi, and many single-celled organisms are made of eukaryotic cells. These cells are larger and more internally organized than bacteria and archaea. They contain structures that divide tasks, move materials, manage energy, and shape the cell from within. This step matters because complex cells provide the foundation for large bodies' specialized tissues and eventually nervous systems. Without them, life may remain rich, durable, and widespread, but mostly microscopic. The origin of eukaryotic cells is one of the major transitions in Earth's history. It does not happen near the beginning of life. Microbes exist for a very long time before clear evidence of eukaryotes appears. The timing remains studied and refined, but the broad pattern is steady. Life begins early in Earth's history, while complex cells arrive much later. This delay may mean that the step is difficult, or it may mean that it needs conditions that take time to develop. With only Earth as an example, the difference cannot be turned into firm odds. It can only be treated as a serious filter in the path from living chemistry to technological civilization. One central feature of eukaryotic cells is the mitochondrion. A mitochondrion is an internal structure that helps the cell release usable energy from food molecules. The leading explanation for its origin is endosymbiosis, in which one cell lives inside another and the partnership becomes permanent over evolutionary time. Evidence indicates that mitochondria descend from bacteria that became integrated into an ancestral host cell. They still carry their own small genetic systems, though most of their functions now depend on the cell around them. This event changes what cells can do. It gives eukaryotic cells a powerful way to manage energy across larger internal volumes. Energy is important because complexity has costs. A larger cell must move materials farther. It must copy more genetic information. It must maintain internal compartments and structures. It must repair damage and control many reactions at once. Bacteria and archaea can be highly efficient, but their simpler structure limits some kinds of growth and internal organization. Eukaryotic cells can build skeleton-like frameworks inside themselves, engulf food particles, move in new ways and host specialized parts. These abilities open paths that simpler cells do not commonly take. They do not guarantee large organisms, but they make large organisms possible. The nucleus is another defining feature. It separates genetic material from much of the cell's working fluid. This separation changes how information is stored, copied, and used. Eukaryotic genomes can become larger and more complex. Genes can be regulated in more layered ways. The cell can process information before turning it into proteins. These features help support specialization. Later, when cells join into multicellular bodies, different cells can use the same genetic library in different ways. Some become muscle, some nerve, some skin, some leaf, some root, depending on the organism. The first eukaryotes do not yet make such bodies, but their internal control makes such futures possible. The environment around early eukaryotes is also changing. Oxygen becomes more available in stages after oxygen-producing microbes alter the planet. Oxygen is useful for high-energy metabolism, though it can also damage cells if not controlled. Mitochondria help use oxygen in controlled reactions. This may connect rising oxygen with the success of eukaryotic life, although the relationship is not simple. Some eukaryotes live in low-oxygen environments. Some use modified energy structures instead of typical mitochondria. Still, Earth's long-term oxygenation likely opens ecological space for larger and more active forms of life. It changes oceans, sediments, and the chemistry of energy. The first eukaryotic life is not an animal or plant in the familiar sense. It is single-celled or forms simple colonies. It lives in water sediments and microbial communities. Some eukaryotes feed by engulfing other cells. Some later gain chloroplasts' internal structures that carry out photosynthesis. Chloroplasts also come from endosymbiosis, when photosynthetic bacteria become permanent partners inside eukaryotic cells. This event leads to algae and plants transforming the way light is captured in many environments. Again, partnership becomes structure. Life becomes more complex not by replacing microbes but by incorporating them. This pattern is important for the paradox because it suggests that complexity may depend on rare combinations of events. A host cell and a bacterial partner must not only meet, They must form a stable relationship. The relationship must survive conflict, transfer functions, divide reliably, and become inherited. Many microbial interactions may occur without producing such a lasting union. If eukaryotic origin requires a narrow path, then living planets may remain microbial for their entire histories. If the path is more common under the right conditions, then complex cells may appear on many stable worlds. Present evidence cannot decide between these possibilities. Complex cells also change ecological relationships. They could become predators at the microscopic scale. They can hunt other cells, form shells, build larger colonies, and create more layered food webs. Predation can drive defenses movement, sensing and new body plans. Even before animals, eukaryotic life increases the range of biological forms. The living world becomes more textured. It includes drifting cells, crawling, cells with flagella cells, with hard covering cells that host photosynthetic partners, and cells that live together in loose groups. These changes still remain mostly invisible from interstellar distances, but they prepare the inner biological ground for larger bodies. The fossil record of early eukaryotes is subtle. Some fossils appear as larger cells, organic-walled microfossils, or chemical traces. Interpretation requires care because shapes alone can mislead. Over time, the evidence becomes stronger. More varied forms appear, and later algae and other eukaryotic groups become clearer. The record shows that the rise of complex cells is not a brief final step before animals. It is a long era of its own. Complex single cells evolve, diversify, and reshape ecosystems before large multicellular life becomes widespread. For a distant observer, a planet with eukaryotic microbes may still appear quiet. It may have atmospheric oxygen or other possible biosignatures depending on the stage. It may show seasonal color changes or ocean chemistry only under ideal observation. It does not send deliberate messages. It does not build machines. It remains a biological world without technology. This is a key lesson from Earth. Even after the origin of complex cells, the path toward technological intelligence is still long and uncertain. This silence of the sky could include many worlds that have reached this stage and no further. Inside this region, the feared solution grows more precise. Life may be common and microbial life may be durable, but the leap into eukaryotic complexity may be a difficult gate. Earth passes through it once in a way that gives rise to all known complex life. The event involves deep cell partnership, energy transformation, internal structure, and long environmental change. Observations indicate that eukaryotic cells appear after a long microbial history on Earth. It remains uncertain whether the same transition is common on other living planets. The inward path now rests on whether complex cells can assemble into bodies large enough for tissues, senses movement, and eventually brains. Inside the world of complex cells, the next inward region is multicellular life. Multicellular life is life made from many cells that remain joined and work together as one organism. This is more than a cluster. Cells must divide tasks, hold their positions, communicate, and allow the whole body to survive. Some cells may gather food, some may form surfaces, some may move, some may reproduce. This division of labor creates new possibilities, but it also creates new dependence. A single cell can often live by itself. A cell inside a body usually belongs to a larger order. Multicellularity appears more than once on Earth. It is seen in animals, plants, fungi, algae, and other groups. This shows that the general idea of cells living together is not impossible or unique to one lineage. Yet large complex bodies with many specialized tissues take time to develop. Simple multicellular forms can be small mats, filaments, sheets, or colonies. They may grow by repeated cell division without complex organs. More elaborate bodies require control over shape, growth, repair, and reproduction. A body must know where its front and back are, where its inner and outer surfaces are, and how different cells become different parts. These patterns depend on genetic regulation, chemical signals, and physical structure. The step from single complex cells to bodies is linked to ecology. When cells live together, they can become larger than many predators. They can reach light, better anchor in place, filter water, or divide work more effectively. Size can be protection. Shape can create new ways to feed. Cooperation can open spaces that single cells cannot use as easily. Yet bodies also need energy. Larger forms must move materials inward and waste outward. They must solve transport. In water, small organisms can exchange gases and nutrients directly across their surfaces. Larger organisms need internal system channels or thin tissues. The body becomes a landscape with distances inside it. Earth's early multicellular record is gradual and incomplete. Some ancient fossils show simple large organisms, soft-bodied forms, and impressions in sediment. The Ediacaran biota, a group of organisms that appears before the major spread of many animal groups, shows that large life exists before familiar animal ecosystems become common. These organisms include forms with quilted surfaces, frond-like shapes, discs, and other body plans that do not always match living groups clearly. Their biology remains debated. Some may be animals, some may represent extinct forms of multicellular life, and some may belong to lineages that leave no close modern counterpart. They show that multicellularity can produce large shapes before modern-style ecosystems become dominant. The later rise of many animal forms during the Cambrian period marks another important stage. In this interval, fossils show a wider range of animals with shells, limbs, eyes, mouths, burrows, and active movement. This is not the sudden creation of life from nothing. It follows long earlier histories of microbes, complex cells, oxygen change, and simple multicellular forms. Still, it marks a clear increase in visible body plans and ecological interactions. Animals begin to dig through sediment, swim, crawl, hunt, defend and sense their surroundings in more direct ways. The seafloor changes as bodies disturb it. Predation becomes more important. Hard parts preserve more easily as fossils. Oxygen likely plays a role in this expansion. Larger animals need energy to move, grow, and maintain tissues. Oxygen allows efficient energy release in cells. As oxygen becomes more available in oceans and atmosphere, it may support more active and larger organisms. The relationship is not a single switch. Oxygen levels change in stages, and animals can live under different oxygen conditions. Nutrients, climate, ocean, chemistry. Genetics and ecological pressures also matter. Observations indicate that increasing oxygen and changing environments contribute to the rise of large animal life. It remains uncertain how each factor weighs in the full process. Multicellular bodies also require development. Development is the process by which a single starting cell becomes a body with organized parts. In animals, early development sets up patterns that guide cells into tissues and organs. Genes control signals, timing, and position. Small changes in these controls can produce different forms. Evolution can then act on body plans, adjusting limbs, shells segments, eyes, and feeding structures. This makes multicellular life deeply flexible once the basic system exists. The same general genetic tools can be reused in many forms. A body becomes a platform for variation. Plants follow a different multicellular path. They use photosynthesis and build tissues that capture light, move water, and support growth. Fungi follow another path, growing through networks that absorb nutrients from their surroundings. Algae create many multicellular forms in water. These separate paths show that multicellularity is not one invention with one shape. It is a set of solutions to the problem of living as many cells together. Some solutions remain simple. Some become forests, reefs, animals, and soil systems. The biosphere becomes layered with producers, consumers, decomposers, and countless interactions among them. For the Fermi Paradox, multicellular life is still not technology. A planet can have oceans full of animals, continents covered with plants and skies crossed by flying organisms while remaining silent to radio searches. It may show stronger biosignatures than a microbial planet because large photosynthetic ecosystems can affect atmospheric gases, surface colors, and seasonal cycles. Yet even a rich biosphere does not guarantee minds that build instruments. Earth has complex life for hundreds of millions of years before technological humans appear. During most of that time, no species sends deliberate signals into space. Mass extinctions add another layer of uncertainty. Earth's history includes events that remove large shares of species. These events are linked to impacts volcanism, climate change, ocean chemistry, and other pressures. They are destructive, but they do not erase life completely. They reshape evolution, opening space for new groups. A planet with multicellular life may experience repeated losses and recoveries. Such events may delay, redirect, or prevent the rise of certain lineages. They also show that complexity is not a stable climb. It is a branching pattern interrupted by environmental change. The existence of multicellular life on Earth demonstrates that complex cells can cooperate into bodies many times. Yet the timing again matters. For most of Earth's history, life remains microbial. Complex cells appear later, and large animal life later still. This sequence suggests that each inward step may need special conditions, long preparation, or rare events. It does not prove rarity beyond Earth. It shows only that one living planet spends a very long time before bodies become large and active. In this region, the silence becomes compatible with many kinds of living worlds. Some planets may stop at microbes. Some may develop complex cells but remain mostly single-celled. Some may grow mats, colonies, plants, reefs, or animals without producing technology. Such planets would be biologically rich and still quiet in the narrow sense of the paradox. They might carry life across oceans and land, but their light would not contain engineered signals. The inward path now rests on the rise of nervous systems learning memory, and the kind of intelligence that can turn a living body into a tool-making presence. Inside multicellular life, the next inward region is intelligence. Intelligence is the ability of a living system to sense conditions, learn from experience, solve problems, and adjust behavior. It is not a single trait with one clear line. Many animals show forms of memory, choice, recognition, communication, and planning. Some use tools, some live in social groups, some navigate across large distances, some learn from others. These abilities arise from nervous systems, bodies, environments, and evolutionary pressures working together. For the Fermi Paradox, this region matters because life can be complex and active without becoming technological. Intelligence has many forms, and only one known lineage builds radio telescopes. A nervous system is a network of cells that carries signals through a body. Simple nervous systems help animals respond to touch-like chemicals and movement. More complex nervous systems collect information from many senses, compare it with memory, and guide flexible action. A brain is a concentrated control center within a nervous system. Brains do not appear in all animals, and large brains are not always necessary for survival. Many organisms thrive with simple behavior. Evolution does not aim toward intelligence. It favors traits that help organisms survive and reproduce in local conditions. If a simple body and simple behavior work well, there is no required path toward a larger brain. The cost of intelligence is high. Nervous tissue uses energy. Large brains require steady food, long development protection, and learning time. A species with a larger brain must gain enough benefit from behavior to balance these costs. Benefits may appear in changing environments, complex social groups, hunting, gathering, tool use, memory, or flexible diets. A stable environment with predictable resources may not reward greater intelligence strongly. A harsh environment may reward speed armor, camouflage, reproduction, or endurance instead. Intelligence is only one solution among many. Earth shows many kinds of animal intelligence. Octopuses solve problems and explore objects with flexible arms. Crows and parrots use memory, social learning, and tools. Dolphins and whales communicate, cooperate, and navigate large marine spaces. Elephants show memory and social awareness. Apes use tools, learn socially, and recognize relationships. These examples show that intelligence can evolve in separate lineages under different conditions. Yet none of these lineages, apart from humans, creates industrial technology. This difference suggests that intelligence alone is not enough. A mind must be paired with the right body environment, energy sources, and social transmission to become technological. Hands matter, but not by themselves. A body that can grasp, carry, shape, and combine objects has an advantage for tool use. Human hands with sensitive fingers and strong control allow fine manipulation. Other animals also manipulate objects. Crows use beaks and feet. Octopuses use arms. Apes use hands. Yet tool use becomes cumulative only when improvements can be preserved and shared. Cumulative culture means that knowledge builds across generations, so later, individuals inherit more than they could discover alone. This requires learning, social tolerance, memory communication, and enough stability for skills to persist. Language is another important layer. Human language allows detailed sharing of absent things, future actions, hidden causes, and social rules. It supports teaching, planning, cooperation, and the transfer of complex knowledge. Other animals communicate in many ways, including calls, gestures, songs, scents, and movements. Some communication is rich and flexible. Still, human symbolic language appears unusual in its range and depth. The origin of language is difficult to study because speech leaves little direct fossil evidence. Anatomy tools, genes, brain structure, and comparison with living species provide indirect clues. Observations indicate that human language depends on a combination of biological and cultural evolution. It remains uncertain exactly how it develops step by step. Social life can support intelligence. In groups, animals track relationships, alliances rank kinship, cooperation, and conflict. Social learning allows useful behavior to spread without genetic change. Care for young can lengthen learning periods. In humans, childhood is long, and learning is deep. Young individuals absorb tools, language, food, knowledge, social rules, and stories about the environment. This long dependence is costly, but it allows culture to become part of survival. A species with strong culture can adapt by changing behavior faster than genes change. Environmental change may also shape intelligence. Ancestors of humans live through shifting climates, changing habitats, and varied food sources. Flexible behavior helps in landscapes where resources move, seasons change, and groups must cooperate. Stone tools show that early humans and their relatives shape materials for cutting, scraping, and processing food. Fire later changes diet protection, warmth, and social life. These developments are not sudden. They build across long periods through many hominin species. Hominins are humans and close extinct relatives. Most hominins do not become technological in the modern sense. Many use tools and adapt well, but only Homo sapiens creates global industrial systems. This fact is important for the paradox. Even on Earth, intelligence appears in many branches, But technological civilization arises only very late and in one surviving species. Dinosaurs dominate land ecosystems for more than 100 million years without producing radio technology. Mammals diversify after major extinction. Primates evolve, then apes, then hominins, then modern humans. This is not a straight ladder. It is a branching tree with many endings. If events had unfolded differently, Earth could have remained full of intelligent animals without any species-building transmitters. The ocean shows another boundary. Dolphins and whales have large brains and complex social lives, but water limits fire, metallurgy, and many forms of material technology. Octopuses manipulate objects well, but they are mostly short-lived and do not build long-term intergenerational cultures like humans. Birds show problem-solving but have different body plans and ecological limits. These examples do not show failure. They show that intelligence must connect to material pathways. A mind must be able to transform the environment in durable ways. It must access energy, make tools that make better tools, and preserve knowledge across generations. The rise of intelligence is therefore not a single gate, but a narrow passage through many conditions. A planet may have animals with eyes, movement, memory, and social life. It may have clever hunters, builders, singers, and navigators. It may have species that learn and teach within local traditions, yet none may cross into technology that can be detected across space. The difference between a smart animal and a technological species is large. It includes anatomy, culture, energy, environment, communication, and historical chance. In this region, the feared solution becomes more grounded. The silence may not require lifeless planets. It may not even require planets without animals. It may reflect the rarity of one particular form of intelligence that becomes cumulative, manipulative, social, and energy-hungry. Earth shows that complex life can flourish for immense spans before such a lineage appears. It also shows that intelligence can be abundant in modest forms without becoming interstellar. Observations indicate that many animals can learn and solve problems, while human technological intelligence remains the only known case of its kind. It remains uncertain whether this path is common on other living worlds. The inward search now rests on whether intelligence becomes technology, and whether technology becomes visible beyond its own planet. Inside intelligence, the next inward region is technology. Technology begins when a living species uses materials, energy, memory, and shared skill to change its surroundings in lasting ways. Simple tool use exists in many animals, but technological civilization is different in scale. It depends on tools that make other tools knowledge that builds over generations and energy systems that extend the power of bodies. It also depends on materials that can be shaped with precision, stored, moved, and combined. For the Fermi Paradox, technology matters because it is the layer where a living world may become visible across distance. A planet with forests, oceans, and animals can remain quiet. A planet with transmitters, engines, lights, and large energy use may leave signs that instruments can seek. Human technology grows from older biological abilities. Hands shape stone, wood, bone fiber, clay, and metal. Eyes guide fine motion. Social learning preserves methods. Language allows detailed teaching. Fire changes food and materials. Agriculture changes landscapes and population patterns. Settlements create new forms of labor and storage. Writing stores information outside memory. Mathematics, astronomy, navigation, and engineering extend human reach. None of these steps is isolated. Each rests on earlier habits and environments. A stone blade, a kiln, a plough, a sail, a furnace, a lens, and a radio antenna belong to one long chain of cumulative change. The first technologies are not detectable from another star. Stone tools do not change a planet's light in a clear way. Fire leaves traces in local sediments. Agriculture changes land cover, but its global signal is modest for most of its history. Cities shine only after artificial lighting spreads. Radio waves enter space only after electrical technology develops. Industrial gases alter an atmosphere only after large-scale fuel use and chemical production. From a distant viewpoint, most of human technological history is invisible. Even on Earth, detectable technology is recent, lasting only a tiny fraction of the planet's age. Radio technology becomes important because it can leak beyond a planet. Early powerful transmissions, radar and broadcast signals move outward at light speed. Yet not all radio emissions are equally detectable. Signals weaken as they spread. Directional beams can remain stronger along narrow paths, but they cover less of the sky. Many modern communications use cables, fiber optics, low-power transmissions, or directed links that leak less energy into space than older broad broadcasts. A civilization may become more efficient and less radio loud over time. It may also choose not to transmit deliberately. The presence of technology does not guarantee a bright and lasting radio beacon. Intentional messaging is even narrower. Sending a strong signal toward another star requires purpose, power, knowledge of a target, and patience. The sender may not know whether anyone is listening. The receiver may not be using the right frequency at the right time with enough sensitivity. A message may pass Earth before a telescope is pointed there, or long before humans exist. Because light travel times are long, communication between stars is slow. A technological society may decide that such efforts are symbolic, scientific, risky, unnecessary, or simply low priority. Science cannot assume that every civilization wants to announce itself. Other possible technological signs are broader but harder to confirm. Artificial lights on the night side of a planet might be visible only with extremely powerful instruments and nearby systems. Industrial gases in an atmosphere may suggest technology if they are hard to explain naturally, but such measurements are difficult. Large structures that collect stellar energy could change the infrared glow of a system, yet natural dust can also produce infrared excess. Mining propulsion or atmospheric modification might leave traces, but many possible signs overlap with natural processes. A technosignature is a sign that may indicate technology. Like a biosignature, it requires context and caution. Energy use is the inner engine of detectability. A society that uses little energy may remain faint. A society that uses large amounts of energy may produce waste heat because no energy process is perfectly hidden. Waste heat appears as infrared radiation. This idea allows searches for very large engineering. If a civilization captures much of a star's energy, the system may become dimmer in visible light and warmer in infrared light. Surveys have looked for unusual infrared patterns. So far, no accepted evidence of such large-scale engineering has been found. Observations indicate that galaxy-spanning or star-enclosing engineering, if it exists, is not common in forms already searched. It remains uncertain whether smaller, colder, more efficient or unfamiliar technologies would be noticed. Technology also depends on planetary materials. A world may have intelligent life, but lack easy access to fire metals, dry land, or concentrated energy sources. Underwater intelligence may have difficulty developing combustion, metallurgy, and electronics, even if it is socially and mentally advanced. A planet with little exposed land may limit mining and controlled fire. A world without abundant metal ores near the surface may follow different paths. A world with frequent disasters may interrupt cultural accumulation. Technology is not only thought, it is thought joined to matter On Earth, the rise of modern technology is connected to geology and stored sunlight. Coal oil and natural gas are fossil fuels formed from ancient life and geological processing. Their concentrated energy supports rapid industrial growth. Other energy sources also matter, including flowing water, wind-wood nuclear reactions, and sunlight. The exact path Earth follows may not be universal. Another world might develop technology through different energy steps, or it might never find a path from tools to industry. A species can be intelligent, cooperative, and skilled, yet remain within local materials for a long time. The detectability window can be brief. Human radio leakage becomes noticeable only recently. Human atmospheric changes are recent. Spaceflight is recent. If another civilization passes through a similar phase quickly, a distant observer must be looking at the right time. A society may reduce emissions, collapse, change form, or move toward technologies that are harder to see. If detectable technology lasts only hundreds or thousands of years, then even a galaxy with many technological species may appear quiet most of the time. Time becomes as important as number. The sky is not only a map of places, it is a record of moments. Technological signals also face interpretation. A strange signal must be separated from human interference instrument error and natural astrophysical sources. Pulsars were once surprising because they produced regular radio pulses, but they are natural rotating neutron stars. Fast radio bursts are powerful brief events now studied as natural phenomena. Many unusual observations become less mysterious after better data. This history teaches restraint. A technological claim requires repeated evidence, independent checks, and no better natural explanation. The absence of such evidence keeps the record quiet. In this region, the paradox reaches the layer most directly searched. The galaxy may contain planets, life-complex cells, bodies and intelligence, but only technological activity creates signals that current searches are designed to find. Even then, technology must be detectable, recognizable, and present during the observing window. Earth shows how narrow that window can be. For billions of years it gives no radio sign. For hundreds of millions of years it hosts animals without machines. For most of human history it remains invisible as a technological world from interstellar distance. The silence may therefore come not from a lack of minds, but from the thinness of the signal-making layer. The inward path now rests on how long such layers endure once they appear. Inside technology, the next inward region is duration. A civilization may become detectable, but the question then becomes how long it remains detectable. Duration is the length of time during which a society produces signs that can be recognized from far away. This may be radio leakage, deliberate signals, industrial atmospheric gases, artificial lights, large energy use, or other changes. A civilization can exist before this window opens, and it can continue after this window changes or closes. The detectable phase is not the same as the whole life of a culture. It is only the part that leaves a trace across interstellar distance. This distinction is central to the Fermi Paradox because space is wide and time is deep. The Milky Way is billions of years old. Stars and planets form across long spans. If technological societies appear but remain visible only briefly, then their signals may rarely overlap with observation from Earth. A telescope receives light from the past. A signal from 1,000 light-years away shows what was happening there 1,000 years ago. A signal from 10,000 light-years away shows a still older moment. Detection requires that the civilization is producing a recognizable sign at the right time in the right direction, with enough strength, while Earth has instruments ready to notice it. Human history shows how narrow such a window may be. Anatomically, modern humans exist for hundreds of thousands of years. Agriculture develops much later. Cities writing and states appear later still. Radio technology appears only in the recent past. Spaceflight is even more recent. From a distant star, Earth is a technological planet for only a tiny slice of its living history. Before that, it is a biological planet. Before that, it is a microbial planet. The detectable layer is thin compared with the age of Earth. If other worlds follow similar patterns, their technological signs may be rare, not because minds never appear, but because visible technology occupies a short interval. Duration can be shortened or lengthened by many factors. A society may grow in energy use and become more detectable. It may also become more efficient and less wasteful. It may shift communications away from strong leaking broadcasts toward narrow beams, cables, or local networks. It may regulate emissions. It may choose not to send interstellar messages. It may build durable instruments that continue after their creators change or disappear. It may spread beyond its planet, increasing its detectable footprint. Or it may remain close to its home world and become difficult to notice. None of these paths is known from another example. Earth offers only an early and incomplete case. The lifetime of a civilization is not only technological, it is also environmental, social, and planetary. A society depends on food, water, climate, energy, materials, health cooperation, and stable knowledge transfer. Natural hazards remain present. Asteroid impacts, large volcanic eruptions, severe climate shifts, pandemics, and stellar activity can affect a civilization. Technological hazards also appear once powerful tools exist. Nuclear weapons, environmental damage, uncontrolled pollution, engineered biological risks and other pressures can threaten long-term stability. These are not certainties. They are possible filters that become relevant only after intelligence and technology have already emerged. A civilization might also change in a way that reduces recognizable signs without ending. It may become quieter by choice or by design. It may use technology that does not leak strongly into space. It may live mostly underground, underwater, or within controlled habitats. It may focus on digital efficiency rather than large external structures. It may send information through channels that are not being searched. It may communicate through brief pulses, tight beams, or methods unknown to present science. These possibilities cannot be used as evidence for hidden civilizations, but they show why non-detection does not equal absence. The search is shaped by assumptions about what technology does. Long duration would make detection easier. A civilization that remains radio bright for millions of years has a greater chance of being noticed than one that signals for only a few centuries. A society that spreads to many star systems would create more possible sources. A society that builds large energy structures would alter its environment more strongly. If such long-lived, expansive, highly visible civilizations were common, the silence would be harder to explain. Current observations suggest that such civilizations are not obvious in the nearby sky or in broad surveys. This does not rule out all technology. It places limits on certain kinds of visible technology. The difference between persistence and expansion matters. A civilization may survive for a very long time without expanding far. It may remain on one planet, one moon, or a small set of habitats. It may value stability over growth. It may face physical, biological, economic, or cultural limits. Interstellar travel is difficult because distances are immense, energy costs are high, and even the nearest stars require long journeys by known methods. Robotic probes may be easier than living travelers, but they still require power, navigation, durability, and purpose. A long-lived civilization does not necessarily become a galaxy-filling civilization. If expansion does happen, its speed matters. Even slow expansion could cross large parts of a galaxy over long timescales if sustained. This is why the absence of clear galactic-scale engineering carries weight in some versions of the paradox. The Milky Way is old enough that a very expansive civilization from an older system might have had time to spread widely. Yet this argument depends on assumptions. It assumes expansion is desired practical, sustained, and visible. It assumes colonies continue to expand. It assumes that signs remain recognizable. Each assumption may or may not hold. The silence can constrain the most expansive scenarios more strongly than the quiet or limited ones. Duration also interacts with recovery. A civilization may suffer collapse but not extinction. Knowledge may be lost and later rebuilt. Signals may stop and begin again. Industrial activity may rise and fall. Climate or resource pressures may reduce complexity without ending the species. Over long times, a planet could have several detectable intervals separated by quiet eras. To distant observers, these intervals would appear as brief flashes in time. Without continuous monitoring, they could be missed. Earth's own monitoring of the sky is extremely recent. The search has not watched the galaxy across long historical spans. It has sampled small windows. The Fermi Paradox becomes sharper at this layer because duration multiplies every earlier uncertainty. The number of stars matters. The number of planets matters. The number of stable habitable worlds matters. The chance of life-complex cells, bodies' intelligence and technology matters. But even after all these filters, a final factor remains. The signs must last. A galaxy may produce technological societies now and then, yet if their detectable lifetimes are short, the sky may remain mostly quiet. The absence of confirmed signals may point not to one impossible step, but to the product of many narrow steps and short windows. In this region, the feared solution is not necessarily that civilization always destroys itself. That would be stronger than the evidence allows. The calmer statement is that lasting detectable technological civilization may be uncommon. Some societies may never become loud. Some may become loud briefly. Some may endure quietly. Some may fail. Some may change beyond present recognition. Observations indicate that no long-lasting, highly visible technological presence has yet been confirmed. It remains uncertain whether this is because such societies are rare, short-lived, hidden by distance, or different from expectations. Duration turns silence into a matter of timing. Stars can shine for billions of years, microbes can persist for billions of years, animals can fill a planet for hundreds of millions of years. Technology may be far younger and less stable. The listening species on Earth stands inside its own first detectable interval, measuring a galaxy whose other intervals may not overlap. The inward search now rests on the pressures that can shorten, soften, or erase a civilization's visible presence. Inside the question of duration, the next inward region is self-limiting risk. A self-limiting risk is a pressure created or intensified by a technological civilization itself, a pressure that can reduce its stability, shorten its detectable phase, or prevent long expansion. This does not mean that every civilization ends in the same way. It does not mean that technology must lead to collapse. It means that powerful tools can change the conditions that support the society using them. The same abilities that make a species visible across space can also make its future more delicate. On Earth, technology increases reach. It allows one species to move energy, materials, organisms, and information at planetary scale. Forests can be cut faster than they grow. Minerals can be removed from deep rock. Rivers can be dammed. Nitrogen can be fixed for crops. Fossil carbon can be burned and returned to the air. Chemicals can be made that did not previously exist in the biosphere. Diseases can travel with transport networks. Weapons can affect entire cities or regions. These changes are not all destructive. Many support food health, warmth, knowledge, and survival. Yet scale creates a new kind of responsibility. A local mistake can become a global pressure. Climate change is one example of a self-limiting pressure. A civilization that releases large amounts of greenhouse gases can alter the heat balance of its planet. Greenhouse gases trap some outgoing infrared radiation and warm the lower atmosphere and surface. On Earth, human activity increases carbon dioxide, methane, and other gases, changing climate patterns, sea levels, ice oceans, ecosystems, and weather risks. The scientific basis is well established. The future severity depends on choices, emissions, feedbacks, and adaptation. This kind of risk is not sudden in the way an impact is sudden. It builds through ordinary energy use, agriculture, industry, and land change. It shows how a civilization can disturb the stable conditions that allowed it to grow. Nuclear weapons show a different kind of risk. They concentrate destructive energy in human control. Their existence introduces the possibility of rapid, large-scale damage through war accident, misjudgment, or escalation. The physical power comes from changes in atomic nuclei releasing energy far greater than chemical explosives. A large nuclear exchange could cause immediate destruction and also affect atmosphere, agriculture, and global systems. The exact outcomes depend on scale and conditions, but the risk belongs to the technological layer. It appears only after a civilization understands advanced physics, engineering, mining, enrichment, delivery systems, and command structures. Knowledge and danger rise together. Biological technology adds another inward pressure. Living systems can be studied, altered, and used. Medicine, vaccines, agriculture, and biotechnology can protect life and improve survival. This same growing control over biology can also create risks if pathogens are mishandled, engineered, or spread through dense global networks. Natural pandemics already exist without advanced technology, but technological society can amplify movement and laboratory capability. Strong public health, safety practices, monitoring, and cooperation can reduce danger. The risk is not that biology always escapes control. The risk is that a civilization with great power over life must maintain care across institutions, generations, and conflicts. Environmental simplification is slower but broad. A technological species may depend on ecosystems while weakening them. Soil pollinators, fisheries, forests, wetlands, and microbial cycles support food and climate. If these systems are damaged faster than they recover, the civilization may lose resilience. Resilience is the ability of a system to absorb disturbance and continue functioning. A society with high resilience can endure shocks. A society with low resilience may appear stable until a stress reveals hidden weakness. Overuse of water, loss of biodiversity, pollution, and land degradation can all reduce resilience. These pressures do not always produce collapse, but they can narrow future options. Artificial intelligence and autonomous systems represent another kind of self-limiting uncertainty. Tools that process information, make decisions, control infrastructure, or design. Other tools may increase productivity and scientific understanding. They may also create risks if goals, incentives, errors, or misuse are not controlled well. The details are debated and many outcomes remain uncertain. The broader point is simpler. As technology becomes more capable, the distance between decision and consequence can shrink. A system can act faster than human institutions can respond. This does not prove disaster. It shows that governance, alignment, oversight, and caution become part of technological survival. Self-limiting risk also includes social and institutional strain. Civilization is not made of machines alone. It is made of trust, cooperation, memory law, education, and shared systems for handling conflict. A society that cannot manage inequality, misinformation, resource stress, or political violence may lose the coordination needed to solve technical problems. Technology can strengthen coordination through communication and knowledge. It can also weaken it by spreading false information, increasing surveillance, accelerating conflict, or concentrating power. These are not purely physical risks, but they affect whether a civilization can remain stable long enough to become a lasting presence. The inward nature of these risks is important. They do not come from the galaxy. They arise after many previous filters have already been crossed. A planet has formed, remained stable, developed life, produced complex organisms, evolved intelligence, and built technology. Then the same technology creates new pressures at planetary scale. This makes the feared solution emotionally heavy, but the scientific form remains restrained. It is not known whether most civilizations destroy themselves. It is not known whether technological societies usually learn to manage their risks. Earth has not existed as a technological civilization long enough to provide a complete example. The evidence allows concern, not certainty. There are also reasons that self-limiting risks may be survivable. Knowledge can reveal danger before it becomes final. Climate science can measure warming. Astronomy can track some hazardous asteroids. Medicine can identify pathogens. Engineering can improve safety. International agreements can reduce certain weapons or pollutants. Conservation can restore habitats. Renewable energy can replace some fossil fuel use. Risk awareness is itself a technological ability. A civilization that can create global dangers may also create global protections. The balance between danger and protection is not fixed. It depends on choices, institutions, timing, and culture. For the Fermi Paradox, however, even survivable risks can shorten visibility. A society under pressure may turn inward. It may reduce energy use, limit transmissions, avoid expansion, or focus on survival rather than interstellar contact. It may recover but lose centuries. It may choose quieter technology because quiet technology is safer, cheaper, or more efficient. It may remain alive while becoming less detectable. In this way, self-limitation does not require extinction. It can produce silence through caution, constraint, or repeated disruption. The most severe version is collapse or extinction, but science cannot assume that outcome. Collapse is the loss of social complexity, not necessarily the end of a species. Extinction is the complete disappearance of a lineage. A technological civilization could experience either neither or several partial setbacks. Its detectable signs might fade while its people survive in simpler conditions. It might rebuild later. It might transform into a stable but quiet form. From many light years away, these different histories may look the same. The signal weakens or never grows large. In this region, the feared solution becomes a possibility about maturity. Technology may be easier to begin than to sustain wisely. A species may learn to release energy before it learns to govern its consequences. It may learn to alter its planet before it understands the full planet. It may become visible at the same time it becomes vulnerable. Observations from Earth show that technological power can create planetary-scale risks. It remains uncertain whether such risks commonly end civilizations or whether they are often managed. The silence in the sky is consistent with many outcomes, including the quiet possibility that visible technological phases are often limited by the burdens they create. Inside the risks that may shorten a civilization's visible life, the next inward region is the limit of detection itself. A signal may exist and still remain unseen. A world may be alive, intelligent, or technological, and still leave no mark that present instruments can confirm. Detection is not a simple act of looking at the sky. It is the work of choosing wavelengths, targets, times, sensitivities, and meanings. Every search is shaped by the tool that performs it. A radio telescope does not hear all radio waves at once. An optical telescope does not see every planet beside every star. An infrared survey does not separate every possible source of heat from natural dust. Instruments make the invisible partly visible, but only within their own limits. The first limit is distance. Light weakens as it spreads. A signal that begins strong becomes faint across interstellar space. If it spreads in all directions, its energy is diluted over a growing sphere. A narrow beam can travel farther with more strength along its path, but then it must point toward the receiver at the right time. Earth's own unintentional radio leakage will be difficult to detect across large distances with present human instruments. Some powerful radar signals are stronger, but they are brief and directional. This means that a civilization similar to present Earth may not be easy to find unless it is close, loud, or deliberately transmitting in a way that crosses Earth's line of sight. The second limit is time. A telescope observes during certain hours, years, or mission lifetimes. A signal may last for a moment, a day, a century, or 1,000,000 years. Brief signals can be missed if no instrument is watching that part of the sky at that frequency when they arrive. Repeating signals are easier to confirm because they can be checked again. Non-repeating signals are harder. A single strange event can be exciting, but science requires caution. It may be interference, an instrument problem, or an unfamiliar natural source. Without repetition or supporting evidence, it rarely becomes proof. The sky may contain brief flashes of many kinds, but the path from flash to confirmed technology is narrow. The third limit is frequency. Radio searches often focus on ranges where natural background noise is lower, or where known physics suggests efficient communication. This is reasonable, but it is also a choice. A civilization might use different radio frequencies, optical pulses, infrared signals, neutrinos, gravitational waves, physical probes, or methods not yet practical for humans. Science cannot search every possible channel with equal depth. It begins with what is known, efficient, and measurable. If another civilization chooses a channel outside present searches, its presence may remain unnoticed. This is not evidence that such channels are used. It is a reminder that search space is large. The fourth limit is meaning. A signal must be recognized as artificial. Nature produces order in many forms. Pulsars create regular pulses. Molecules create spectral lines. Stars flare. Planets produce auroras. Black holes and neutron stars create extreme radiation. Dust clouds glow in infrared light. A pattern that seems unusual at first may later become understood as natural. The history of astronomy includes many surprises that were not signs of life, but new physical phenomena. This makes caution essential. A true technological signal must stand apart from natural causes, human interference, and instrument error. Recognition may be as hard as detection. Human interference is a strong local problem. Earth is surrounded by satellites, aircraft transmitters, radars, and electronic systems. Radio observatories must work to identify signals that come from human technology rather than space. Reflections, side lobes, and unexpected equipment behavior can create false candidates. Some signals appear promising until their timing, direction, or frequency shows a terrestrial origin. The more technological Earth becomes, the more clutter it adds to its own listening environment. Quiet zones, careful calibration, and space-based instruments can help, but they do not remove all difficulty. Planetary detection has related limits. A distant planet is usually hidden in the glare of its star. Transit methods find planets only when their orbits line up. so they pass in front of the star from Earth's viewpoint. Radial velocity methods need precise measurements of stellar motion. Direct imaging works best for large planets far from their stars, especially young warm ones. Earth-sized planets in Earth-like orbits around Sun-like stars are difficult to study. Even when a planet is found, its atmosphere may be hard to measure. Starlight passing through a thin atmosphere carries a small signal. Clouds hazes stellar activity, and instrument noise can blur the result. Detecting life or technology in such data is far harder than detecting the planet itself. Biosignatures and technosignatures both require context. Oxygen in an atmosphere may be produced by life, but under some conditions non-living processes may also create oxygen. Methane may come from biology or geology. Industrial gases may suggest technology if they are unlikely to arise naturally, but detecting them at interstellar distances is difficult. Artificial lights would be faint beside starlight and reflected daylight. Waste heat from large energy use might be confused with dust, unless the pattern is strong and clear. A surface color could come from minerals, ice, vegetation, or other materials. Each possible sign needs a chain of evidence. A single measurement rarely carries enough weight. Search coverage is still small compared with the full problem. The Milky Way contains vast numbers of stars, and only a fraction have been searched deeply for narrow signals across broad frequency ranges and long observing times. Many searches focus on selected nearby stars, known exoplanet systems, or regions of special interest. This is sensible because observing time is limited. It also means that non-detection must be read carefully. It says that certain kinds of signals are not found in certain parts of the search space. It does not say that all signals are absent everywhere. There is also the problem of assumptions. Many searches are guided by human technology because that is the only example available. Humans know radio lasers, chemistry, atmospheric pollution, heat, and large structures. These guide practical searches. Yet another technological species may develop along different lines. It may communicate mainly within its own system. It may use low-power methods. It may value quietness. It may be active beneath ice, underwater, underground, or in habitats that leave little planetary signature. It may produce signs that humans would classify as natural because the pattern is unfamiliar. These possibilities are not claims. They are boundaries around certainty. Detection limits can make a populated galaxy appear empty. If life is mostly microbial, its signs may be faint. If intelligence is rare, its signs are sparse. If technology is brief, its signs are temporary. If advanced technology becomes quiet, its signs may fall below present thresholds. If signals are directional, most miss Earth. If they are distant, they fade. If they are strange, they may not be recognized. Each limit reduces the chance of discovery. Together they create a wide region where absence of evidence remains different from evidence of absence. Yet detection limits do not erase the paradox. They soften it. If highly visible civilizations were common nearby, long-lived and expansive, some signs might be expected to stand out more clearly. The fact that none has been confirmed places pressure on those simple expectations. It suggests that at least one part of the chain is limiting. The limit may be life complexity, intelligence, technology, duration, visibility, or search reach. Present observations cannot choose one with certainty. They can only narrow some possibilities and leave others open. In this region, the silence becomes partly a mirror of the instruments. The sky may be quiet because there are no voices nearby. It may be quiet because the voices are weak, brief, distant, hidden, or unlike what current searches seek. Science stands between those meanings with careful tools and incomplete coverage. Observations indicate that no confirmed technosignature has yet been found in the searched ranges. It remains uncertain how much of the total possible range has been meaningfully examined. The inward path now reaches the final uncertainty where all filters combine into the quiet answer that may be true. Inside the limits of detection, the final inward region is the combined answer. The silence of the sky does not need one single cause. It may come from many narrowing steps acting together. Stars must have planets. Planets must be stable enough. Chemistry must become life. Life must persist. Simple cells must become complex cells. Complex cells must form bodies. Bodies must develop intelligence. Intelligence must become technology. Technology must become detectable. Detectable signs must last long enough and travel in a direction, and form that instruments can receive. At every step, the path can continue, pause, or end. The Fermi Paradox lives in the full chain, not in one link alone. The solution that scientists may regard with concern is not always the most dramatic one. It is the quiet possibility that lasting technological civilization is uncommon. This statement is narrower than saying life is rare. It is also narrower than saying intelligence is impossible. A galaxy may contain many planets with oceans, many worlds with microbes, some worlds with complex life, and even some worlds with intelligent animals, while still having very few societies that become visible across interstellar space for long periods. In this form, the answer is not an empty universe. It is a universe where most life remains silent. Earth makes this possibility understandable because Earth itself is silent for almost all of its history. For billions of years, it carries no radio technology. For most of its living history, it is ruled by microbes. For long periods after animals appear, no species builds machines. Human technology rises very late. The time between the first life and the first radio signal is immense. If another observer had watched Earth at nearly any earlier time, Earth would not have answered as a technological world. It may have shown biological hints under ideal observation, but no deliberate signal, no industrial pattern, and no clear engineering. This does not prove that Earth is typical. A single example cannot define the galaxy. It only shows that the path can be long, uneven, and dependent on many transitions. The first life may appear early on Earth, but complex cells appear much later. Large animals appear later still. Technological humans appear at the end of a branching history shaped by climate geology, extinction, chance, and adaptation. Other planets may move faster, slower, differently, or not at all. The known evidence supports caution. It does not support certainty that the galaxy is sterile, nor certainty that it is filled with hidden societies. The feared answer can therefore be stated calmly. The universe may be good at making planets less certain, at making life slower, at making complexity rarer, at making technological intelligence, and poor at keeping it detectable. Each stage may be possible, but the full sequence may be uncommon. Even if no single step is extremely rare, the product of many modest filters can create a quiet sky. A small fraction multiplied by another small fraction becomes smaller still. Over galactic time, some successes may occur, but they may be separated by distance error, signal type, and duration. This combined view also explains why the silence has not ended the search. If the absence of signals came from one obvious impossibility, research would narrow quickly. Instead, every layer remains partly open. Exoplanet surveys show many worlds. Planetary science shows that environments can be varied and sometimes stable. Chemistry shows that organic building blocks are widespread. Earth shows that microbial life can begin and endure. Biology shows that complexity can arise, though slowly. Animal behavior shows that intelligence has many forms. Human history shows that technology can become detectable, but only recently. Each fact adds possibility. Each uncertainty preserves the silence. The word solution can be misleading because the Fermi paradox may not have a single solved form. It is a framework for comparing expectation with observation. The expectation comes from the size and age of the galaxy. The observation is the absence of confirmed evidence for other technological societies. Between them are many assumptions. Some assumptions may be too generous. Planetary abundance is well supported, but the abundance of Earth-like stability is less certain. The chemistry of life is promising, but the origin of life is unresolved. Microbial success is known on one world, but the rise of complex cells may be difficult. Intelligence can evolve in many ways, but technology requires special material and cultural pathways. Detectability depends on behavior physics and timing. The inner uncertainty also carries humility. Human technology is young. Human searchers are young. Radio astronomy, exoplanet discovery, atmospheric study, and technosignature research are still early compared with the age of the galaxy. The absence of a confirmed signal is meaningful, but it is not final. It rules out some simple expectations more strongly than others. It weakens the idea that loud, nearby, long-lived, expansive civilizations are common and easy to find. It does not rule out quiet civilizations, rare civilizations, distant civilizations, extinct civilizations, non-technological intelligence, microbial biospheres, or signs outside current methods. The same silence can support different scientific attitudes. One attitude focuses on rarity. It treats each step as a possible filter and asks which filters are hardest. Another focuses on detection limits and asks how much has actually been searched. Another studies risk and asks whether technological phases tend to shorten themselves. Another studies life's origin and asks whether biology begins easily. These attitudes do not need to exclude one another. The final answer may be distributed across them. The sky may be quiet because life is not everywhere, complexity is not automatic, intelligence is not enough, technology is brief, and detection is hard. The calmest version of the feared solution is that Earth may be unusual in one or more important ways. It may be unusual because life begins here. It may be unusual because complex cells arise here. It may be unusual because animals' intelligence, language, hands, fire, metals, fossil fuels, and culture connect in one lineage. It may be unusual because technological society appears at all. Or it may not be unusual in those earlier ways, but unusual only in being close enough and timely enough for its own instruments to notice nothing similar nearby. The unknown remains broad. There is no need to turn this uncertainty into despair. A quiet sky is not the same as a meaningless sky. It is a measured condition that guides careful questions. It asks how planets form, how atmospheres survive, how chemistry becomes life, how cells become complex, how bodies evolve, how minds arise, how societies manage power, and how instruments can search better. The paradox is unsettling because it places human civilization inside a large silence. It is scientifically useful because it connects many fields into one patient investigation. At the deepest point, the silence becomes a reflection of scale and fragility. The Milky Way is vast, but each living world, if it exists, may depend on small balances of heat, air, water, rock chemistry, time, and behavior. A civilization able to ask about the silence may be a brief and delicate layer on top of those balances. It may be common enough to arise more than once, or rare enough that each case matters greatly. Observations indicate that no confirmed technological neighbour has yet been found. It remains uncertain whether the reason lies in the stars, the planets, the first cells, the long biological path, the shortness of technology, or the limits of search. The final region of the paradox is therefore not an answer shouted across space. It is a quiet boundary where knowledge ends, inquiry continues, and the night remains full of stars without a confirmed reply. The silence now settles into a wider calm. The stars remain what they are. Distant suns held in the dark by gravity and time. Around many of them planets may move in steady paths. Some may be bare stone, some may be wrapped in gas, some may hold oceans under ice or clouds above quiet continents. A few may carry chemistry that has crossed into life. Fewer may carry cells that have become complex bodies, that have become aware, and minds that have learned to shape matter. The Fermi Paradox does not close with certainty. It rests in the space between what is known and what is not yet measured. Observations show a universe rich with stars and planets. They show no confirmed technological neighbour. Between these facts lies a long chain of conditions, each one narrow in its own way. The chain may break early on many worlds. It may continue quietly on others. It may reach intelligence without machines, or machines without long visibility. Earth remains the only known living world and the only known technological world. Its history is long, mostly quiet and delicate. Microbes endure for billions of years. Animals arrive late. Technology arrives at the edge of the present. From this single example, the galaxy cannot be judged completely, but caution grows naturally. Lasting visible civilization may be rare. It may be brief. It may be hidden by distance, timing, or form. The night sky keeps its silence without explaining it. Its darkness is not empty. It holds light dust worlds and unanswered possibility. Science listens with patient instruments, and each careful search adds one small boundary to the unknown. The final feeling is not certainty, but stillness. The question remains open beneath the stars, quiet enough for sleep and large enough to wait.